Now we're going to look at scientific methods. Okay, like I said in class, you have covered this a few years ago in physical science, where you talk about how you come up with a theory or a law, what a hypothesis is, and that kind of thing. We're going to start off this scientific methods idea with a little bit about alchemy and kind of backtracking a little bit. So the first thing I've got written down here is that chemistry comes from alchemy. Okay, the word chemistry comes from the word alchemy. All right, you have practical alchemy, which was working with metals, dyes, glass. People were trying to figure out how things worked, how metals interacted. They had a lot of kind of interesting ideas about what different things came from. They had a lot of interesting names for stuff, okay? This is kind of, you're talking a long time ago, like, 13th, 14th, even 1500s, okay? You also have mystical alchemy, which is the whole idea with trying to turn stuff into gold. It kind of switched gears a little bit, all right? When you look back to those kind of 1500s, okay, you shifted, or the ideas kind of shifted. So we actually kind of shifted to science, all right? People actually started discussing topics and doing experiments. So instead of just trying to figure out philosophically why something happened, they actually would discuss a topic and then do an experiment about it to try and figure it out. So they formed some new societies, okay, and they were actually shifting their ideas to try and base any kind of conclusion of what they call the natural world, base conclusion of the natural world, which means the world around you, okay, on evidence. And when we talk about evidence, we mean an experiment. I put EXP, I'm lazy. Okay, we mean an experiment, not just an idea that you sat and kind of thought about and philosophical reasons behind why something happens. Okay, a couple hundred years later, we had a guy named Antoine Laurent Lavoisier. I'm just gonna write his last name. I believe he was French. Okay, in the 1700s, he kind of actually shifted it even more. He did a huge contributions to chemistry, okay? He looked at how things burned, and he was trying to figure out exactly what makes something burn. And through some different observations and realizing that when you burn something, it actually gains mass. He was trying to figure out why that is. And he did all these experiments, and he actually, so he was looking at burning, okay, and why things burn. And he actually ended up kind of learning a lot about oxygen and nitrogen. And he actually figured out that you need oxygen in order to get something to burn. So you start off with these kind of just working with a dye and a metal. You're shifting towards actually working with experiments and trying to get data. And you kind of keep going on them with our elements. When we get to the periodic table then later on, you're talking about Dmitri Mendeleev and how you're organizing elements. They first had to come up with these elements, and Lavoisier was a big part behind that. All right, so using these different concepts that all these different scientists use, okay, they use the scientific method. All right, they started off with observations. All right, whether they would be a qualitative observation or a quantitative observation. Okay, observations are what you see. So you've got to first off look at what you see and try and figure out, okay, here's what I'm seeing. Now, then we go to the next step, the hypothesis. Well, what you see can be either a qualitative or a quantitative observation. If you're looking at a qualitative observation, it's going to sound kind of stupid, but you're looking at a quality, all right? So that means you're dealing with something that's not a number. So maybe a color, okay, or how something reacts, all right? That's a qualitative piece of data. You're dealing with a quantitative piece of data. That's then the opposite, quantitative. Okay, you're dealing with a quantity, which hence the name. Okay, or a number. Okay, you're dealing with some kind of mass, a volume, something where you have actual numbered physical data. Okay, mathematically that I can look at. All right. So you start off with these observations, either qualitative or quantitative, and we work through and we try and form a hypothesis, all right? And hypothesis is just a proposed explanation for an observation. All right. Now these hypotheses, okay, have to account, so it must account for what is being observed. So if you have a piece of data or you see something and it doesn't have anything to do with your hypothesis or it doesn't fit your hypothesis, then you have to change your hypothesis. So if data doesn't fit, okay, the next step then, we're kind of going through this graph here. We started out with an observation, piece of data. We form a hypothesis, okay. I want to look at, I see that the sky is blue. I form a hypothesis that the sky is blue because the earth is leaking blue dye. I don't know, okay. Now I'm going to form an experiment. Try and prove that this is actually what's happening to the earth, all right. So experiments are used to test a hypothesis, right? And if you want to have your experiment actually accepted, okay, you have to test it a lot of times. So it's kind of a side note here. To have accepted results, so for somebody out in the scientific community to actually believe you, you have to, or you must be able to produce the same results over and over. Otherwise, it's not reliable. There are two variables. This is the last little portion at the bottom of this page. Okay, you have an independent variable and a dependent variable. Okay, independent variables are the variables in an experiment that you have control over. So you have control. They are what you change. A dependent variable, hence the word in it is depend, okay? A dependent variable is actually what you measure in the experiment. And measure in the sense that it's what's being affected. It's what you didn't know ahead of time, okay? So they are directly affected, or they depend on the independent. So independent variable is going to say, okay, I'm going to run 100 meters, then I'm going to run 200 meters, then I'm going to run 300 meters, and I'm going to time myself. First time I run 100 meters, I run 12 seconds. Then I run 200 meters, and I run it in 30 seconds. Then I run 300 meters, and I run it in 60 seconds. This is my independent variable, and this is my dependent variable. It's what I was measuring, what I wasn't sure I was going to get. Okay? Last two things. Scientific law. All right, a scientific law is a concise statement that summarizes your results of many observations and experiments. So it's a summary of the results of many, that's the key word there, got to be a lot, many observations and experiments. Similarly, I'm going to explain here in a second, a theory, they tell me, is a well-tested explanation for a set of observations. And honestly, don't they just sound like the same thing? Okay? So you have a well-tested explanation for a set of observations versus a summary of the results of observations and experiments. And if you look up at the chart here that you have on the other side of your paper, notice how you don't have one and then the other. An experiment can produce a law, or an experiment can produce a theory. A lot of times people will consider a theory to be something that you're kind of testing over and over again, and maybe a law to be something you've tested over and over again and you kind of come up with. But you'll also find other people who will say that theories deal with things that don't have math in them, and laws are dealing with things that have math. Someone else might say that a theory is how nature works, and a law is what nature does when you do something to it. Honestly, they're really about the same kind of thing. All right? One does not predicate the other. You don't have one before the other. Okay? The last little side note is you'll often find when you're doing the scientific method here, if you're working with somebody else, there's going to be all kinds of conflict. When we start and research the atom later, okay, there's all kinds of conflict about if I'm working with somebody, well, who publishes first? Who gets credit? What are we published? Okay, do I get my name on it? Do you get your name on it? That kind of thing. So you'll see that kind of pop up, and there are some really interesting stories actually behind who gets credit for stuff and who gets forgotten, unfortunately, sometimes. So we'll look at that as we move on throughout the year.